In this video, we will discuss a few problems on Archimedes' principle. In particular, we will show you how to solve problems on buoyant force calculations using Archimedes' principle. We will look at problems of calculating buoyant force and other parameters that are dependent on it for systems such as floating ice block. We'll also look at a problem that relates true and apparent weight of an object in a fluid to the buoyant force that acts on the object. Problem 1. A large block of ice floats on a freshwater lake as shown. What minimum volume, the volume of this ice block that is, must the block of ice have for a 50 kg person, that is this person right here, to be able to stand on it without getting her or his feet wet? Now, density of water is 1000 kg per cubic meter, and density of ice is 920 kg per cubic meter. Let's sketch the free body diagram for this system. So you have this person, so that is the ice block, and the person is standing on it. So the free body diagram for this person ice block system is as follows. Now you have the person's weight acting like that, and that is 50 times gravity. You have the weight of the ice block, let's call it M ice G, and you also have a buoyant force acting upward, let's call it FB. Since the person and the ice block are floating on the surface of that freshwater lake, whatever buoyancy or whatever buoyant force that is acting on the system must be greater or equal to the total weight of the system. So the weight of the person plus the weight of the ice block. Note that this expression is purely from the free body diagram, and we have not looked into Archimedes' principle yet. That is exactly what we are going to do next. Archimedes' principle states the buoyant force, in this case, equals the weight of the water displaced by that ice block. So the weight of the water displaced by this ice block. We know the mass of water equals the density of water times the volume of water, but in this case the volume of water displaced must be the same as the volume of the ice block itself. So we write the Archimedes principle here quite simply as density of water times the volume of, let's call it the ice block, V sub I, times gravity. Substituting this expression inside this inequality, namely on the left-hand side of the inequality, we get the following result. Note that the G will just get cancelled, and this inequality becomes the density of water, volume of ice, greater or equal to 50 plus the mass of the ice block. Now we know the mass of the ice block must be the density of ice times the volume of the ice block. By moving this term to the left-hand side, we simply get the volume of the ice block multiplying the density of water minus the density of ice must be greater or equal to 50. Since we are interested in minimum volume the block should have, we can simply take the equality part of this inequality and write the minimum volume is quite simply 50 over the density of water minus the density of ice. So the density of water is 1000, the density of ice is 920, 1000 minus 920 is 80, which is 0.625 cubic meter. So that is the minimum volume the ice should have, and that solves the problem. Problem 2. An iron block of density 7800 kg per cubic meter appears 180 newtons lighter in water than in air. Find the volume of the block, and what is the true weight of the block take the water density to be 1000 kg per cubic meter. So in the first diagram, the object is simply hanging in air. So this W here is the true weight. And in the second diagram, the object is obviously below the surface of water. And you have two forces acting on this object, the weight and the upward buoyant force. So now the apparent weight is obviously the difference between the true weight and the buoyant force. We are told that the object, the iron block, appears 180 Newton lighter in water than in air. That means the true weight minus the apparent weight is indeed 180 newtons. And from this equation, we see that 180 newtons has got to be the buoyant force. So we can simply write the buoyant force as 180 newtons. And since Archimedes' principle tells us that the buoyant force equals the weight of water displaced by this iron block, we can equate this 180 newtons to the weight of the water displaced by the iron block. The mass of the water displaced equals the density of water times the volume of the water displaced. However, we know that the volume of water displaced must be the same as the volume of that iron block. So we can simply write 180 equals the density of water, the volume of that iron block, times gravity. And we can solve for the volume of the iron block as 180 divided by the density of water, which is 1000, times gravity, which is 9.81. And that will give you a volume of 0.0183 cubic meter. Now we can proceed to determine the true weight of the block. Now the true weight of the block, that is this, is quite simply the mass of that iron block times gravity. Now the mass of the iron block is the density of iron times the volume of the iron block that we have just determined times gravity. So the density of iron block is given 7800. The volume is 0.0183 and gravity is 9.81. And when you calculate that, you get 1400 newtons for the true weight of the block. And that solves the problem. Problem 3. A cubical brass block, that is this one right here, with sides of length 50 centimeters. So it is a cubical block like that, and each side has a length of 50 centimeters. It floats in mercury. So this is the mercury. So what fraction of the block is above the mercury surface? So this portion here is what we want to determine. So let's label the fraction of the portion of that block above the mercury surface as V block with an arrow up, and the portion of block below the mercury surface as VB down. So when you add the VB up plus VB down, that's going to give you the total volume of the block. Now since this block is floating, so the weight of that block, let's call it mass of the block times gravity, equals the buoyant force, the upward buoyant force on the block. So we can simply write the buoyant force on this brass block equals the weight of that block. So this is from the free body diagram. We also know that Archimedes' principle states that this buoyant force equals the weight of the mercury displaced by this block. So we write the weight of the mercury displaced is the mass of the mercury displaced times gravity, and that equals the mass of the block times gravity. The mass of the mercury displaced equals the density of mercury times the volume of the mercury displaced. Now what is the volume of the mercury displaced? The volume of the mercury displaced must be the same as the volume of the block which is below the mercury surface. So it is VB with a down arrow. Now we know that G get cancelled, so we don't have to write that. And that equals, now the mass of the block. The mass of the block is the density of that brass. Let's call it rho B. And the volume, the total volume of the block, which is this. Let's rewrite this term in terms of the volume of the block above the surface and the total volume of the block. And if we do so, this equation becomes the density of mercury times the volume of the block, subtract the volume of the block above the mercury surface. And that equals the density of the brass times the total volume of the block. Moving terms around, you see that VB minus VB up over VB equals rho of brass over rho of mercury. And this side is quite simply 1 minus VB up over VB. The density of brass is 8,600, so 8,600. The density of mercury is 13,600. So since this equals that, we can solve for this term, which is the fraction of the block that is above the mercury surface, which will simply become 0.368, or we say 36.8% of the block is above the mercury surface. Part B. If water is now poured on the mercury layer, what must be the depth of the water layer in order for the water surface to rise to the top of the brass block? So this part is mercury, and the water is even with the top surface, so this is water. So let's assume that this height here, that's the depth that we want to calculate, h. So this must be 0.5 meter, because each length is 50 centimeters, converted into meters, 0.5, minus h. So that is just that. Now since the block is floating, the weight of the block, which is mass of the block times gravity, must be balanced by a couple of buoyant forces. One is the buoyant force due to the mercury level, and the other one is the buoyant force due to the water level. So let's calculate one term by one term. The buoyant force due to the mercury level equals the weight of the mercury displaced, and that will be the mass of the mercury displaced times G. And the mass of the mercury displaced is the density of mercury times the volume of this part of that cubical brass, which is the surface area, is quite simply 0.5 squared times the depth of a 0.5 minus h, and then you multiply that with gravity. Just remember, the lower part of that block, which is inside mercury, has a surface area of 0.5 times 0.5, and the length is quite simply this length. Likewise, the buoyant force due to the water level is the mass of the water displaced times gravity. Now the mass of the water is the density of water times the volume of this portion of that block, which is again 0.5 squared times h, and then multiplied by gravity. Since the entire block can be considered floating, the weight of the block, which is the mass of the block, times gravity must be the same as the sum of this term and that term, as we discussed earlier. The left-hand side is the weight of the block, which is just the mass of the block times gravity. The first term on the right is the buoyant force due to the mercury level, and the second term on the right is the buoyant force due to the water level. Now all the densities are given, and all we have to do is to solve for h. This is density of water, density of brass, which is the density of the block, and density of mercury. G will get cancelled, and when you solve for h, you get 19.85 centimeters, and that solves the problem. Thank you for watching.